So this lecture is going to cover some of the highlights from the chapter on hypothesis testing with inferential statistics. So hypotheses. First, we need to know what hypotheses are. So hypotheses articulate what the expected relationship is between variables. And so these stem from your research questions, as we've talked about many times what your research questions are. They're grounded in theory or conceptual models. So, what is the theory? I've asked you several times in your assignments, sort of what is the theory or the assumptions? And it's tested using data and inferential statistics. So testable hypotheses define the groups that are being compared, the variables that we're comparing, and what the expected relationship is. So I'm sure that you remember making hypotheses probably from science class, even in early secondary education. And so here, these hypotheses are going to take a little bit more of a scientific and a statistical context in this chapter. There are two types of hypotheses that we're going to talk about. The first one is the null hypothesis, and it states that there will be no relationship between two variables. And so this is something important to remember. It states that there will be no relationship between the two variables. An alternative hypothesis states that there will be a relationship between the two variables. And so that relationship can either be directional or non-directional. So here's an example of a null hypothesis. There will be no relationship between height and weight in adolescent boys. That would be a null relationship because it's stating that there's no relationship between height and weight. An alternative hypothesis, there's an example here, directional or non-directional. So the directional alternative hypothesis would be height will be positively related to weight in adolescent boys. And so that really means taller boys will weigh more. The non-directional hypothesis says there will be a relationship between height and weight, but it doesn't indicate what type of relationship that would be. So here we have a positively a hypothesis that says it will be positively related, where in the non-directional alternative hypothesis, it doesn't indicate, it says there will be a relationship, but it doesn't indicate which direction the relationship will be. Hypotheses are tested with inferential statistics. So the null hypothesis is always the hypothesis that we test. So we're always testing the null hypothesis, and remember that is that there is no relationship. So if we reject the null, this means that the researchers believe that the variables are statistically associated with one another. Okay, so if we reject the null, we're rejecting the statement that there is no relationship. That means that we believe that there is a statistically associated relationship between the variables. If we accept the null, which is also stated as failing to reject the null, this means that the researchers don't believe that the variables are statistically associated with one another. So that means that the null hypothesis then is correct. The decision to reject or accept the null hypothesis is based on two different things. One is the p-value. So I know that you have seen these values in some of the literature that you've read, and so now you're going to learn exactly what that means. So the p-value is the probability value, and this is the probability that the results of the statistical test were obtained by chance alone. This is computed from the data and is not known until we actually complete the statistical test. So remember, this is the probability that the results that we got were just by chance alone. So generally in healthcare, we're looking for a p-value to be fairly small. We really don't want chance alone to determine the effectiveness or determine whether or not we implement certain types of treatment just based on chance. So that's why in a lot of the medical literature, the p-value generally has to be 0.05 or even 0.005. We want it to be fairly small. The alpha level, is the p-value that is defined by the researchers as statistically significant, and this is defined before any statistical tests are conducted. And so alpha levels are often 0.1, 0.05, or 0.01, as I indicated above here, depending on how much we are willing to let chance alone determine the outcome. I would say in many of the studies, you're going to see this p-value of 0.05, but in some healthcare studies, you're looking for something a little more specific, and it might be a 0.01. I don't see 0.1 too often in healthcare literature. So the p-value is the probability that the tests were obtained by chance, and then the alpha level is where we define as statistically significant. So this is just a little stats meme that I came across. Roses are red, violets are blue. If you were a null hypothesis, I would fail to reject you. So basically, a lot of times this lecture falls around Valentine's Day, so I thought it was a fitting little meme to help you to remember null hypotheses. So question, which type of hypothesis is the following statement? People who are immunized against the flu will be less likely to contract the flu than those who are not immunized. So the answer is that this is a directional hypothesis. And so the reason this is directional is, so our choices were null hypothesis. So we know it's not null hypothesis because this is stating that there is a relationship between immunization against the flu and contracting the flu. So those two variables. So they're saying there is a relationship, and so it's not null hypothesis. So then we have directional, non-directional, and an alpha level hypothesis. Well, this isn't one of the choices that we talked about, so we can automatically eliminate it there. But we did talk about directional and non-directional. And so the reason that the answer is directional is because that the hypothesis states that the relationship between immunization and contracting the flu is expected, but it also states the direction of that hypothesis. So it states the direction by saying less likely. That's how you know there's a direction. It will be less likely. So they're stating the direction of that relationship. The other thing we need to know is types of errors. And so we're going to talk about type 1 and type 2 errors. Type 1 error is when we reject the null when it's true. So in other words, we say there's a relationship between the variables when one really doesn't exist. A type 2 error is when we accept the null when it's false. And so in other words, that we say there's no relationship, which is the null, when one really does exist. In any study, we'll never know if we have one of these types of errors, but you do need to know the difference between type 1 and type 2 errors. So here is an example. I can't remember if this is from your book or not, but a type 1 error is similar to a false positive. So we have a type 1 error telling this man that he is pregnant, and a type 2 error, which is a false negative, telling a woman who clearly is pregnant that she is pregnant. And so that is a way to remember type 1 and type 2 error. Type 1 error, rejecting the null when it's true, you want to look at the probability of making a type 1 error, and that's defined by the alpha level. So the alpha level of a study determines the probability of making a type 1 error. So given an alpha level of 0.10, we'll make a type 1 error 10% of the time. A type 2 error is referred to as beta, and it's when we don't reject the null when it is false. The power of doing statistical tests. So the power of a test is its ability to detect statistically significant differences. So when we run some of these statistical and inferential statistics, the power of the test is really its ability to find those differences. Mathematically, we define the power of 1 minus beta. And power is a function of the alpha level, the sample size, and the population effect size. So when you're talking about, the power, it equals a relationship between alpha sample size and the population effect size. And there are numerous statistical packages that will help you compute the power of a study. So this is a meme from the Wahlberg Statistical Memes collection that can be found on social media. And here it says, I heard you upped your sample size, more power to you. And that just helps us to remember that the function of power in a analysis, if you up your sample size, a lot of times you increase the power of your study. So question, if there is in fact a relationship between immunization and contracting the flu, and the researcher concludes there is no relationship, what type of error have they committed? So there is a relationship between immunization and contracting the flu, and the researcher concludes that there is no relationship. So the answer is a type 2 error. And that's because a type 2 error is when we say that there's no relationship, but one does exist. So the researcher has concluded there's no relationship, but in reality, one actually does exist. So that's your type 2 error. Here are the 6 steps for hypothesis testing. The first thing you need to do is state the hypothesis, and in the both null and alternative form. You're going to define the alpha level and choose the appropriate statistic. You're going to make sure your data meets the assumptions, and we'll talk about some of those. There's different assumptions for different tests. You're going to compute the parameters that are being compared. So are you comparing means? Are you comparing percents? You want to make sure those are computed. You're going to compute the test statistic and obtain the p-value of the statistic. So some type of statistical test and get the p-value. You're then going to compare the p-value to the alpha level and state a conclusion. So here's an example of the 6-step process. So if we are conducting a one sample z-test, a one sample z-test is used to compare a sample mean to a population mean. So let's say we have the mean of a group of children, and let's say we have their mean weight. And we're going to compare that to the population. So what's the mean weight of a 10-year-old? And we have a group of 10-year-olds. Obviously, we don't have every 10-year-old, but let's say we have a classroom of 10-year-olds, and we have their mean weight. So this example will ask, do women who attend a local church health fair have significantly different mean BMI than women in the general US population? So we're looking for a difference here. Is there a difference? So the data comes from a sample of women attending a health fair at a church. So step 1, state the hypothesis. So our null hypothesis is the mean BMI of women attending the health fair will not be significantly different than that of the US population. The alternative hypothesis, which is non-directional, is the mean BMI of the women attending the church health fair will be significantly different than that of the US population. And this is non-directional here because we haven't said that the mean BMI of the women attending the church health fair will be significantly greater or significantly less than the US population. If we would have had something that said that, it would be a directional hypothesis. We're going to define our alpha level and choose the appropriate statistic. So the alpha level for the study is 0.05, which is commonly seen in healthcare studies. This would mean that if the value of the computed statistic occurs by chance 5% of the time or less, the null hypothesis will be rejected. So we don't want it to, be by chance. We're going to give ourselves 5% 5% error that it happened by chance. And the test we're going to use is a one sample z-test. And this is the type of test you would use when comparing a sample mean to a population mean. The rejection region. So this next figure that I'll show on the next slide shows the rejection reason for a one sample z-test in a non-directional hypothesis. And a non-directional hypothesis also can be called a two-tailed test. So test results that fall in the bottom or top 2.5%, like the outer 5%, are considered statistically significant. This is our rejection region. If the value of the computed one sample z-test falls within the region, we reject the null. Most often, and this, is something you want to work with a statistician on, but the current standard is to use a two-tailed test, even with a directional hypothesis, although it is more technically correct to use a one-tailed test. So here is the figure that they're talking about. So this is the rejection region is into this area. So if the number falls within the calculated statistics falls within the rejection region, then we reject the null hypothesis. Step 3 is to make sure that the data meets the assumptions of the statistic. And so every statistic has different assumptions that have to be met. In a one sample z-test, the data are normally distributed and the population mean and the standard deviation are known. So those are the two assumptions that have to be met in order to use this test. And so the data we have does, and so we can proceed with the test. And then you're going to compute your parameters. So what we need is the mean BMI, and we have 48 women in the sample, and it has the standard deviation is 3.4. So when we compute the statistic, you are then going to obtain the p-value. So this is your equation for a one sample z-test. So z would equal the mean minus the mean of the population. So you have two mean scores. This is the one from your data set, and this is the one that you have from your whole entire population. So we're talking about like the population of the United States. And you're going to take that and divide it by the standard deviation divided by the square root of n, which is the number of participants in your sample. So here you can see this played out. 29.2 minus 27.9 over 5.4 divided by the square root of 48. And so this value becomes 1.67. So your p-value, so the p-value statistic equals 1.67. And then you're going to compare the p-value to the alpha level that you've set. So the computed statistic is 1.67. Since this does not fall into the rejection region, it would need to be either less than negative 1.96 or greater than 1.96. Remember, we have the curve and there you have your rejection region. The associated p-value is greater than 0.05. And that's because it does not fall in the rejection region. And we conclude that there is no statistically significant difference in the mean BMI between the women in our sample and the US population mean. True or false? If the difference between two groups is large, we can say that it is statistically significant, even if our computed p-value is not less than the alpha value that we set for the study. True or false? Answer is false. Statistical significance is defined by the computed p-value and the preset alpha level. It doesn't rely on the difference between the two groups being large. There could be a large difference between the two groups that is not significant. So I wanted to show you a quick example here that's from your homework to give you a little bit of start here. You're going to compute a z-test and find the one-tailed and two-tailed p-value for each of the following situations. You're going to write up your results in a single sentence. You're going to use an alpha level less than or equal to 0.05. So in this example, this first one, the mean BMI for US men is 26.8. With a standard deviation of 4.6. You have data from a sample of 25 men and who are attending a diabetes health promotion program, and the mean BMI of the sample is 31.3. So what you're going to do is you're going to write out your equation. You're going to take the mean of your sample, which is 31.3. So we get that from here. And you're going to subtract the population mean, which is right here. And then you're going to divide that by the standard deviation. So standard deviation is 4.6. And you're going to divide that by the number in your sample. And so that's 25. And then so you just calculate that out and you get a number. And I'm not sure what that number is off the top of my head. I don't have my calculator here. But that is how you plug those things into the equation. And then you will need to decide if that number meets your definition and is statistically significant.